Okay, so we are going to have a last lecture on the machine learning. Okay, so go for it.
Okay, well, we saved the best for last. So thanks for sticking with us all the way till the end. So the plan for today is we're going to finish talking about applications of normalizing flows and also GANs to calorimeter simulation, fast calorimeter simulation. And then I'll be telling you about two ways that normalizing flows, two ideas we've had for applying normalizing flows to anomaly detection and model-independent searches for new physics. Okay. So let me start. I'm going to switch between the Blackboard and the screen, and then back to Blackboard and then the screen. So sorry if that is annoying. But yeah, so I will want to show some plots and things. All right, so Gregor in his lecture mentioned the CalOGAN paper, and also it's a public data set. Okay, so here I will give you some references. Okay, and this is Paganini, de Oliveira, and Nachman. And okay, so these works are just companion works. It's a PRL, PRD pair, like a short and a long version of the same thing. And they had the nice idea to fit a GAN to Lecture04 simulations, right? So the problem they studied was E plus photons and pions. Whoa, thank you. Okay, so E plus photons and pions. And for simplicity, they just studied a toy Atlas eCal. Okay, so some simplified version of the Atlas electromagnetic calorimeter. And of course, Atlas also has a hadronic calorimeter, but just for simplicity, they just wanted to see if they could reproduce the response of the Atlas eCal, or a toy version of it, to incident particles of these type. Okay? And so, as we said last time, and also in Gregor's lecture today, the state of the art for this in terms of physics accuracy is a program called Lecture04. So it's very accurate, but very slow. And just to put a number on it, at least on their computer, they showed that it is about 1.7 seconds per shower on a CPU. Okay, so it takes 1.7 seconds per shower on a CPU, and the LHC needs to generate literally billions of these showers, because every event has, hundreds of particles hitting the calorimeter. Every particle has to have showers, and then they have to generate millions or billions of events. So it really adds up. Okay? Good. So, and then they considered electrons, photons, and pions, 100,000 showers each, generated using Lecture04. Okay? And with energies ranging from 1 to 100 GeV, sampled, I forget now if it's sampled uniformly or logged uniformly. Anyway, you can check that. Okay, so this data set, I want to emphasize, is public and downloadable. It's not very big. So that's a nice thing that they did, is that they made their data set public, and that's an increasingly popular trend, I think, which is a good trend, I think, people making their data that they use for their papers and their studies public. So anyone can go and download this and play around with it if you like. Okay.
Able to have a true Geon simulation as well as their data, both of them?
No, I don't, actually good question. I don't know if they, I'm not sure they made public their Calogan generated showers. They did make public their code though. So you can train, as Claudius and I did and I'll describe, you can train their Calogan out of the box and they made sure it works. So you can then generate your own showers. Yeah, good. Okay, so this is a description of the data set that I'm going through. And let me tell you what their ecal look like, okay? So the ecal that they set up has 3 layers. And each layer, so 3 layers. So this is the Atlas-ish ecal. Okay, so it has 3 layers, and layer 1 has dimensionality 3 by 96. Layer 2 has dimensionality 12 by 12, and layer 3 has dimensionality 12 by 6. I'm not completely sure why they do things this way, but it has to do with, this is called, so each layer is like this. Okay, so there's 3 layers, yeah? Each layer is like an image. Okay, and the particle comes in here in this picture, and it comes in here in this picture. Okay? I'm not exactly sure why they voxelize it like this. So these are called voxels, because they're 3-dimensional pixels. I don't know why they choose to voxelize it like this. I think it has to do with the typical shower. They want to have a higher resolution image in the first layer, maybe because the typical shower leaves most of its energy there. And then the later layers are less important. Okay, good. So if you count these products up, you find that this ecal has a total of 504 voxels. And then the goal of this surrogate modeling or generative modeling task is to learn and sample from P of x conditioned on the incident energy, where x lives in R 504 and are the voxel energy deposits. Does that make sense? So every time I sample from this big probability distribution, I get 504 numbers. Those numbers are the energy deposits of a shower in this ecal. Okay. Oh, and I guess it's also conditioned on particle type. So they didn't train one GAN. It would have been interesting actually, but they didn't train one GAN to do all 3 particles at once. Like we were talking yesterday about a GAN that's conditioned on MNIST digits, and it'd be better to train one GAN that's conditioned on all the MNIST digits than 10 different GANs. Well, they chose to train 3 different GANs, so 1 for each particle type. Okay. So anyway, this was, I think, a very nice work, and it was the first application, I think it was the first application of GANs to our field, and it was just a nice idea that we could speed up Lecture04 simulations this way. A very nice idea. Good. And then, yeah, so what they showed is fitting their Calogan to this data. They could achieve something like an order 10 to the 5 speed up in generation time. Now I know people quibble over this propaganda 10 to the 5 because they did it on a GPU, Giant was on a CPU. How do we really compare these things? I'm not an expert on that. But I think they achieved something. Like, it's definitely faster. Okay. Now, good. So how do they, okay, it's one thing to have a fast GAN, but how do they judge the quality of these generated images? Okay, so that's the question that Gregor mentioned in his lecture. is how do we generate, okay, we generate a bunch of showers. Let's say we generate 100,000 showers of our own, and we compare them against the reference sample that we want to reproduce. How do we judge the quality? Well, what they did in this paper is to compare histograms and average images and individual images. I think that's all they did. So yeah, so to judge the quality of these images, let's see, I'm on a Blackboard space, but let me erase a little bit, I guess. Okay. So quality metrics. So histograms of features. For example, the brightest pixel in the image, or the pixel histogram, the distribution of pixel energies or voxel energies for the center voxel in the image, or the ratio between the brightest and the second brightest voxel energy, things like that. Okay, so histograms of features. They can look at average images, etc. Okay. Good. So in terms of the quality, this was like the first work, and it was groundbreaking. But I would say the quality was not amazing by eye. And so what I want to tell you about next is some work that my postdoc Claudius and I did applying normalizing flows to the same problem. And what we found is that the flows do a much better job. And we came up with one more metric, which we called the ultimate classifier metric, okay, which is a binary classifier between generated and reference images. Okay, so it's actually maybe it's kind of an obvious thing because, okay, what if the generated images are exactly matching the reference images in distributions in the full phase space, then what do you expect this ultimate classifier metric to give you? Like, what do you expect the AUC to be? Let's see if anybody has learned anything. So if the generated and the reference images are really drawn from the same distribution, what will the AUC of this classifier be? Or accuracy of this classifier be? What will the AUC score be? Will it be like close to 100%, which means it's very easy to tell them apart? Or will it be close to 50%, which means it's very hard to tell them apart? Okay, so thank you. So good, so the idea of this ultimate classifier metric is that it should be sensitive to the full likelihood ratio. Okay, so this ultimate classifier metric should be sensitive to P reference of X divided by P gen of X. Okay, and if these two distributions, that's the Neyman-Pearson lemma, right? So if the distributions match, then the classifier score will be 1 on everything. And then the AUC will be 50%. Okay, so can't tell them apart.
This metric is better than like a K divergence type of the metric?
I mean, yeah, so good. So I think this gives you access to the KL divergence, basically. Otherwise, how would you compute it? Because you don't know this or this a priori. Yeah, yeah, so this is how you access that. And yeah, you might ask, why didn't people consider this ultimate classifier metric before? It seems like instead of looking at all these histograms and things, you should just do this classifier because it's sensitive to everything. And the reason, as far as we could tell, also in the ML literature, is that even these GANs that generate perfect looking faces and things, they fail this ultimate classifier test. Those images are actually 100% separable from the real ones. And maybe that's because they have little artifacts in them that aren't relevant for real world uses. But we really care about these distributions a lot. So good. So what we found is if you apply this ultimate classifier metric to the CalOGAN, they're 100% separable. And then when we trained our flows on this, we found it's less than 100% separable. Okay, so now let me show you some plots from this paper. Okay. Wait, that's not the right screen. Oh, that's there. Great. Okay, so this is the work we did pretty recently with Claudius, where we fit basically this math that I was telling about yesterday. We fit a math to the CalOGAN data set. And let me just show you some. So this is this made block I told you about yesterday, right? So this is the building block of the math, okay? And instead of using an affine transformation, we use something more complicated, which I won't have time to tell you much about. But remember, the affine transformation is this linear transformation between x and z. And instead, you can use a more expressive transformation called rational quadratic splines that the machine learning people came up with. So we use that. This is just reiterating what the CalOGAN geometry is. Okay, and then, yeah, so we actually decided to have a two-step flow. So these are the sort of choices you make when you work on one of these things. Sort of like Gregor was saying, like the sky's the limit, these are Lego building blocks, and you can choose to put together or design your own architecture. These are choices you make. So we chose to actually have one flow, here you can see here, which learns the total energies deposited in the three layers, okay, as one probability density, so just a three-dimensional probability density. And then we chose to train a second flow that would learn the shapes, so the normalized shapes in the three layers. So the voxel, all 504 voxels normalized by the energies. So we found that this empirically worked well for us. Okay, so now you see what the sort of architecture is of these normalizing flows. The flow 1 starts with a three-dimensional base distribution and then can give you the three deposited energies sampling if you go this way. Or you can start with the energies from the Géant data and it'll give you the probability density. So this is density estimation and this is sampling. And we then, flow 2 has a similar structure, right? Good. And so let me just show you some of the results that we got. So this is now you can see, this is for positron showers. Layer 0, I don't know if you can read that, but layer 0, layer 1, layer 2. This is the average. If you take all 100,000 showers and you just add them all up, so you make one average image out of them in each layer. This is what you get. The middle one is what you get for Géant. Okay? Down here is what CalOGAN gives, which, like I said, is not great by eye, right? But, this was state of the art for a while in 2017. And this is what CalOFlow gives you. Okay? So the flows seem to learn distributions much better than the GANs. To me, this is not surprising, because the GANs never really learn the distribution explicitly. They only learn it implicitly. And so it's very easy for the GAN to get the underlying distribution wrong. All these problems that Gregor mentioned, like with mode collapse, these are symptoms of the instabilities that you get when you train GANs. Okay, so this is a similar story for photon showers. This is Géant4, this is CalOFlow, this is CalOGAN. And the pions, actually CalOGAN had a lot of trouble with because actually pions don't deposit hardly any energy in the ecal. They're supposed to deposit all their energy in the hcal. So it was actually hard for the GAN to model these long tails, sharply peaked at 0 and then long tails that pions would give you. Okay, but the flow has no trouble with that. Okay, and good. So we could skip over. These are like individual images. So here are some histograms. Okay, so the solid color here is Géant. So the shaded in is Géant. The solid histogram is the flow, and the dashed histogram is calogan, is the GAN. Again, you see the GAN is not doing a great job of getting the distributions right. Okay, good. So that's the so that's for electrons. This is for photons. Again, the flow hits the distributions pretty much all on the head, and the GAN is pretty off in almost every place. So that's, I think, an emerging theme in this generative modeling or surrogate modeling, at least for our field, I think. I'm biased, but I would say that the flows are a much more powerful and effective tool than the GANs. Now, you go look in the literature, and flows have trouble making realistic images. Okay? So there's a trade-off here, I guess, between getting individual examples that are really nice and getting distributions that are right. Yeah, so the flows are good for distributions, I think, and that's what we're seeing here. And that's what we care about, I think, in our field. Okay, so more plots, more plots. So the histograms all look, I think, very nice in the flow versus the Géant. And so now let me skip to the classifier metric. Okay. All right. So here is the classifier metric that I described, applied to the GAN and applied to the flow. So this is what I was saying, is that the GAN gives you 100% classifier score. This is the AUC here. You can ignore, this is some other metric called JSD, which, it's also very high. But so let's just focus on the AUC for a moment. So the classifier score is basically perfect for the GAN and the versus Géant. And that's just because the GAN produces these artifacts which are really out of sample compared to Géant. So the classifier can pick up on, we call them tells. Like when you're playing poker and the person has a tell, then you know exactly what they're thinking. So the GAN produced tells which are not in the Géant reference data set. The classifier can learn that. But CaloFlow is less than 1. So that's what we were excited about, is these metrics are less than 1 for CaloFlow. We also explored different ways of pre-processing the data, and a DNN versus a CNN. We found actually a CNN didn't classify as well as a DNN, which we were surprised by since these are images. And maybe our CNN just wasn't powerful enough. But also maybe these images are so sparse that a CNN actually has trouble with its filters actually learning anything. So yeah, so I would focus on the DNN column here, and I would focus on unnormalized, which is more physical. If you pre-process, you can get a slightly different answer. Anyway, so that's the milestone I think that flows have demonstrated in this surrogate modeling task, is that they seem to be superior. Yes?
What's the second number in the cell?
Yeah, so I didn't have time to explain it, but it's another metric for whether two distributions are the same, called JSD, the Jensen-Shannon divergence that I think Gregor mentioned it in his lectures. Yeah. So again, a score of 1 is good, and a score less than 1 well, score of 1 means that they're very easy to tell apart, and a score less than 1 means they're harder to tell apart. Yeah, the two distributions.
So do you see a room for improvement? I mean, you are close to 0.5, but
yeah, exactly. So this is not right. Good. So definitely there should be a lot of room for improvement because this is 0.847, which is not 0.5, right? So maybe a better density estimator or better approach could get closer to 0.5. Exactly.
So do you know why the electron is worse than photon, or like a showering, or 0.66 on the other hand, E plus and pi plus, and
Yeah.
It has a more shower, right? Than photon.
We tried to interpret these numbers a bit, but it's not, we didn't do an in-depth study like of what did the machine learn sort of thing. So I can't give you a very clean answer, I would say. Yeah, yeah, yeah. But yeah, we were just happy to get any number less than 1. So apparently this is, I think this might be the first time any generative model has passed this, when I say passed this classifier test, gotten a score less than 1. At least I'm not aware of any case in any of the literature, including the ML literature, where any generative model got a score less than 1 on a reasonably high dimensional task like this. Okay, and the last thing is the timing of these things. So here's where you see, so Lecture04 needs 1.7 seconds per shower. Calogan gets you the factor of 10 to the 5 or 10 to the 4 as I advertised. And right, and then CaloFlow, it gets 36 milliseconds per shower. So it is faster than Lecture04, but it's slower than the GAN. And can anyone tell me why, if you were paying attention in my last lecture, why this CaloFlow is not as fast as the GAN? Remember, I told you that CaloFlow is based on this MAF, or mass autoaggressive flow architecture. Sorry? Good, so good, yes, exactly. So the MAF, remember the MAF is slow to sample by a factor of D, the dimensionality of the space. D here is 504. So the MAF is slow by a factor of 504 to sample compared to the speed of density estimation. So that's why, in fact, if you calculate the ratio between these two numbers, you get a number very close to 504. Okay. Good, so that's where we left it in this paper, is we got very impressive, I think, performance on the distributions and the ultimate classifier metric, but it wasn't as fast as Calogan. So we actually wrote a second paper, which, where we figured out how to train this inverse autoaggressive flow. And for reasons maybe I don't have time to, let's see, when did I start? 2:30, no, 3:15, okay. Yeah, so yeah, there's challenges of training this inverse autoaggressive flow because it's very slow to density estimate. But we need to density estimate in order to train it. So it's 500 times slower to train the IAF than the MAF using the log likelihood. So instead what we realized, there's an interesting machine learning literature paper called probability density distillation, or teacher-student models. And so we were very excited when we found this paper. Again, you can do a lot of our research by Googling. And so what we found is this cool idea that you can fit the IAF, the inverse autoaggressive flow, to the mass autoaggressive flow. So the IAF is like a student, and the MAF is like a teacher. Let's see, do we have a nice diagram of that? Maybe not. So yeah, you can fit, instead of fitting the IAF directly to the data, which would be 500 times slower, you can fit it to the MAF, to the teacher. Okay, so, okay, maybe this diagram this is a very complicated looking diagram, but what it's saying is that if you start with a data point, you can map it through the teacher, the MAF, to the latent space. That's fast. And then you can map it back using the student, using the IAF. That's also fast. And then you get another point in the data space. And if the IAF really is the inverse of the MAF, these two things should agree exactly. So you can use that to fit the IAF to the MAF. Yes?
I'm sorry, I have a very, very stupid question on this that always bothers me.
There are no stupid questions, except from you.
If we have the density encoded in the map, why do we really need the second training to get the student? Shouldn't there be some trick of doing, let's say, a numerical operation, an analytic transformation of one thing into the other without having to go through a second training? It really bothers me on some level.
Yeah, so we thought hard about that, and we couldn't see a way. I think what you're asking, what Gregor's asking, in case you couldn't hear, is how come, if we have the teacher, the math, and it's an invertible transformation, and we have all the steps of the transformation, and all of its parameters and everything, how come we can't just easily invert that to get the IAF, right? And get an analytic, so like basically, and I think the answer is that inside the math are these DNNs. The DNNs are not, easily, tractably invertible. Does that make sense? So yeah, so you'd have to figure out a way to invert the DNN. So maybe you could try to fit, inside there you could try to fit some inverse DNN sort of thing. Yeah, but we couldn't get, I don't remember if we really tried that or not, but yeah, we didn't go down that road. Yeah. So yeah, so we actually got this to work, I think, pretty well by fitting the student IF to the teacher math. And good. So, oh yeah, I forgot to mention, there's another quality metric that you have for flows, which you don't have for other, like GANs. If you have access to the exact, to the likelihood, to the density estimate, you can compare different density estimators to each other because they should, the better one should give you the smaller negative log likelihood. So yeah, that's another metric you have. Okay, so these are now student, Shant, and teacher. And you see the student looks pretty good. It matches the teacher and it matches Shant. For E+, for photons, and for pions. The average images look good. There are no artifacts or anything that catch your eye. The distributions also look pretty good. They're not, let's see, they're not perfect. So they do overshoot a bit maybe sometimes. But anyway, overall they're, I think, very nice. And here's the classifier scores for the student and for the teacher. So these are taken from our first paper, and these are now calculated for the student. And they're also passing the classifier test.
Why is that the new number is better than old number?
How did the student surpass the teacher, right? Should not be possible. We were also confused by this, and we didn't have a great answer. We just thought that maybe the teacher was a little bit off from Lecture04, and maybe just randomly the student got lucky. So the student's going to be a little bit off from the teacher. So maybe it happened to be between the teacher and the reference. Just got lucky.
Chinese saying, I don't know how to translate this old saying to English. In Korea, 청출어라. So you get you find that the better students out of full of people. But that is for the E+, right?
Yeah, right. And in other cases, they're worse. We expected them to be worse. So yeah. So and for 2 of the 3, they're worse. And 1 of them, they're better. So yeah. So the message here is that it still passes the classifier test. And then let's look at the timing now. So now we see with the teacher, we had our 36 milliseconds. And with the student, we get our factor of 500 gain that we wanted, or that we were promised. And so now it's on the same speed level as Calogan. You can also see how long it takes to train these things. So on our GPU, at least, Calogan took us 200 minutes to train, and Caloflow with the teacher and the student altogether took maybe a factor of 2 or 3 more to train. So you could say, well, that's bad, but then take into account the fact that you might need to generate 10 billion showers, and here's a comparison of the total time, training plus generation time, for Lecture04 versus the flows and the GANs. And after you've generated, say, more than after you've generated more than 10,000 showers, the initial training time cost is worth paying, at least by this rough estimate. Yeah. Okay. So I guess, yeah, this is just a illustration of some of the cool things that you can do with normalizing flows and how powerful they are. And I would say that's one of the sort of hot topics these days. Any questions about this? Yes, please.
Can you remind me one more time why the student is, the speed of students is more faster?
Okay, good. So let's see. I don't have any. I can try. Okay, so let me try to explain it without the blackboard. Yeah. So the math was very slow. The teacher in this case was very slow to very fast to density estimate. So density estimate means we map data to noise. And that transformation could all be done with one big neural network under the hood. Whereas to go from noise to data, the teacher math has to do it sequentially. So it has to first invert the transformation from x1 to z1, and then only after it's done that, it'll invert x2 to z2, or I'm doing the other way around, sorry. z1 to x1, and then z2 to x2. It has to do them sequentially. So that's the factor of D, or 500 in this case. And the IAF is the opposite. So it parameterizes everything in terms of Z, so it's one big neural network when it's going from Z to X. And when it's going the inverse, X to Z, it has to do it sequentially 500 times. Does that answer your question? You look confused still.
Yeah, I need to understand by myself. Okay, thank you.
Okay. Basically, in one direction, the teacher is one big neural network, and it can be done in a vectorized, parallelized way on the GPU. In the other direction, it has to it really has to step through every coordinate and do its inverse one at a time. So it's 500 times slower because of that.
So it means reason that we have benefit in the GPU system.
Yes.
Right? Oh, okay,
yeah, if it wasn't for the GPU or the vectorized computation of the GPU, then maybe this would be a different story.
By parallelizing the computation.
Right.
Okay,
The GPU can do this big neural network with all of its outputs, 500-dimensional outputs. It can do that parallelized.
Okay.
Yeah.
Okay.
So on a CPU, I guess the story would be totally different.
Okay, thank you very much.
Yeah. Good. Okay, any other questions about this stuff? No? Anybody in Zoom? Okay, let me just advertise then, and then I'll wrap up the discussion of this surrogate modeling. Claudius and I and others, like Gregor is a co-organizer, and Ben, we were inspired by like the fact that there's all these different approaches you can apply to the same problem. And we wanted to know like what are the pros and cons of each, and just like with the top tagging thing, we wanted to have a common data set or data sets to benchmark everything on. Like Gregor was doing his thing with the ILD, and we were doing our things with the Calogan, so we wanted to have a nice common data set to try everything out on. So we decided to start a new challenge, the Fast Calorimeter Simulation Challenge, started this year. And we produced 3 different data sets. And actually, it's interesting, the first data set is like okay, so Calogan was like a toy atlas data set. This data set is the actual atlas calorimeter. Just one slice of it, just one ADA slice of it. But it's what they use to develop their fast simulation. They have a version 3 of the fast simulation, which actually uses a WGAN for part of it, for a small part of it, I would say. And this is what they trained their WGAN on. So they agreed to make it public for this challenge, or they were already going to make some of it public, and they agreed to make more of it public, I guess, for this challenge. And so the challenge is to do what I was just describing on this data set and the other 2, and produce the best possible showers that you can. And just like with the top tagging, it's going to be a friendly thing, and maybe there's no clear winner, and some things are better than others at different aspects. So it'll be very interesting to compare all these things. And then we're going to, everyone should, of course, who wants to participate, should publish papers on the archive and put out their own work, I'm saying. And then we'll collect everybody's results together and do one big comparison paper. So it's really modeled after the top tagging challenge. And the prize, if you like, for having the best model for dataset 1 would be that Atlas might be inspired to use it. In that case, your work will live on in the next, 10 billion showers that Atlas generates for run 4 or whatever. So yeah, so and then the other two data sets are bigger. So this one has about 500 voxels, and these have order 10 times more and 100 times more. So 100 times more starts to get to the size of the data set that Gregor talked about, and this is something intermediate to that. Okay, these don't correspond to any real detectors, but are based on some Lecture04 examples that you can find. And yeah, so the challenge would be, like, if you just try to take the thing I just told you about, the callow flow, and apply it to data set 2 and 3, you can't even fit it into computer memory. So something, we need to innovate more if we're going to do data set 2 and 3. Again, can fit these things, I think, or it won't fit them very well. And then you could try like BibAE or something. So yeah, so this challenge is ongoing, and if you're at all interested in this stuff, I highly encourage you to try it out. You can download these data sets and play around with them. And we hope to at least have people present some preliminary or partial results at ML for Jets, which is going to be at Rutgers in November. So yeah, that's the last thing I wanted to advertise about that. Okay, any last questions about calorimeter simulation? Yes? Yes. So I think I wasn't being too fast with that. I mean, again, so the question was, why could again fit into computer memory for data sets 2 and 3, but a flow can't? And I would say the answer is that the GAN, if you remember, the GAN samples from, it's not an invertible transformation. So it samples from typically a much smaller latent space than the data space. So even though the data space might have 40,000 voxels, you could do a GAN with 100 dimensional latent space if you wanted, or 1,000. Yeah, so that's, it turns out that is more economical for the memory, yeah. Okay, all right, so if there are no other questions about that, I'm gonna switch now to talking about anomaly detection. So let me stop this, raise that. Let's see, I have about half an hour left. So Gregor is going to save me a lot of time because he already set everything up nicely, and it reminded you what the LHC Olympics data set looks like. So I'm going to sort of pick up where he left off and talk about the other kind of anomaly detection, which is, so remember, 2 types of anomaly detection. So the first type is outliers. And you might say you want this to be 0, so out of sample anomalies, right? Or at least very small. And the other is over densities. And if you think for a second, what does it mean to be an overdensity? Overdensity relative to what, right? So to be an overdensity, so you have your background distribution, and you want your data distribution to be overdense relative to that, right? To be like peaking somewhere that the background is not, let's say. And so we have two ingredients here. You have the background density and the data density, right? And so if you think for a second, what is the optimal way to say that you have an overdensity? You'll come to the conclusion that it is nothing other than the likelihood ratio. So if you can think about what this means, one way to think about this is, remember the Neyman-Pearson lemma again. This would be the result of doing a classifier between background and data. Okay? Or you could think of it as this is the optimal score for the hypothesis test. It's going to sound weird when I say it. Is my data more like the background or more like the data? Of course, how could the data not be like the data, right? So it's not actually the data here. It's like a model for the data, yeah, and a model for the background, let's say. So so how much does the model for the data differ from the model for the background? That's what this is saying, okay? And so we've started calling this thing the idealized anomaly detector. Because that's, if you're doing these over densities, that's the best you can do. Okay. One other point about over densities, which I think is a nice feature of this way of looking for anomalies, which Gregor, I think, already mentioned, is that, so if you give up on looking for outliers and you just say, let me give me all the places where this is small. So let's say it's less than some anomaly threshold, maybe. Well, as Gregor said, with a change of variables, I can take a given data point and move it around, because this is not invariant under coordinate reparameterizations, right? It's a density, right? P of x dx is invariant, but P of x is not, right? So this is not reparameterization invariant, this criterion. So depending on how I represent my data, a given data point, a given event, could be an outlier or anomalous or not. It's kind of an iffy way of doing things if you ask me. Meanwhile, the case here, consider this, right? If I change variables, I'll have a Jacobian here, and I'll have the same Jacobian here. They'll cancel out. So this anomaly score is reparameterization invariant. Okay, doesn't mean that we should stop doing things this way, because maybe it would take a total, maybe your threshold is like 10 to the minus 14 or something. So it would take a totally crazy, or sorry, maybe your threshold is something and then you have an event which is 10 to the minus 14 in some coordinate frame. It might take a totally crazy transformation that's, you know, unphysical or something to move that event above your cutoff. So yeah, doesn't mean we should stop doing things that way, but that's a nice feature of this story. Okay, good. So now, how are we supposed to get P background? That's the question, right? How the heck are we supposed to get P background? So first of all, what is P background? What is the background here? We're doing searches for new physics, right? So what is the background we're talking about? No, what? Standard model, right? So background equals standard model, but of course, nobody knows what P standard model is in the space of collider events as recorded by the detector, right? There's too many things that happened between the hard process, which maybe we can calculate with some accuracy, and then the detector response, right? So it's just intractable. So P background of X is intractable. But the classifier trick is a powerful trick, right? So as Gregor said, one approach would be to do background equals Monte Carlo events. Like maybe you run MadGraph and then Pythia and then Lecture04, and you produce a sample of events. And if you understood all the cross sections of all the standard model processes and you added them all up with the right proportions, you could make a sample of events that's supposed to look like what you get at the LHC, right? So if you could do that, then you could train a classifier between Monte Carlo and data and learn R of X. And this is an idea that's been explored by some people. And you know, like Gregor said, it's perfectly viable. It's as good as your Monte Carlo is. Yeah. So could work if Monte Carlo is good enough. And it's just a feeling, or maybe it's from experience, that the Monte Carlo is generally not good enough across all the phase space of all the kinds of events that you could get. But maybe in some corners of phase space, or some final states, like purely leptonic or something, electroweak, the Monte Carlo might be good enough. Yeah? So that's a thing that's being actively studied right now. Okay, what I want to tell you about in the remaining time are alternatives to this. Okay, so if the background could be learned somehow from the data. Of course, that would be circular. It can't be the same data that appears there, right? So what we need is something called a control region, right? Control region data. So maybe I'm looking for my new physics here, and over here in some kinematic variable, maybe call it M or something, I don't know. Over here, you say there's no new physics by assumption. And over here, you say there could be new physics. Okay? So if P control region equals P background of X in the signal region, if my control region really is perfect model for the background in the signal region, then what could I do to get my anomaly, overdensity anomaly score? If the control region data is a perfect match for the background in the signal region, what could I do? What would be the trick in that case? So let's say here I have just background, and here I have background plus a little bit of signal. And it's the same background events. Or not the same exact events, but drawn from the same distribution. Then what could I do to get my likelihood ratio? Somebody knows the answer, I'm sure. You could say it. You can train a classifier, right? So if this is true, then you can train a classifier between control region and signal region. And then you would learn R of X equals P data in signal region and P background in signal region. Okay, what I just described to you is, this is called classification without labels. And we heard about it in Ben's seminar on the first day of the week. It's pronounced koala. Okay, and in a nice paper by Ben and collaborators. Oh yeah, so this is an example of what we would call weak supervision. Okay, so in a nice paper, they showed how to apply this idea to a bump hunt. Okay, so, and that's going to be sort of the context in which we'll be working for the rest of what's left of this lecture. Okay, so what's a bump hunt, right? So Gregor already introduced the concept. For a bump hunt, we might have some invariant mass where new physics could be resonant. And maybe the invariant mass of the signal lives here, okay? And then you say, well, then there's no signal in the sidebands, right? So this is the signal region. And these are called sidebands. And the sidebands give us the control region in this case. Okay, so that's how we would define our signal region and our sidebands. But actually, what are we even doing here? So what is X? So X might be some totally orthogonal space, set of features. As Gregor said, our data is actually very high dimensional. Traditionally, we've done one-dimensional bump hunts. Yeah? And what we're describing here are now sort of like multi-dimensional bump hunts that are possible because of machine learning. Okay? And so the idea that you should imagine is besides MJJ, every event has other interesting features. So let's be concrete. The R&D data set from LHC Olympics looked like this, where these are QQ bar, let's say, QQ bar. Okay, so that's the signal events, yeah? So for this kind of signal, so this mass of the Z prime, okay, so these are highly boosted. So I get two what are called fat jets, okay? And so MZ prime, this is MJJ. Okay, this is J1, this is J2. So the Z prime mass is going to live in MJJ. Okay, that's the resonant feature. Okay, what are the other features? What are X? Well, if this is the class of things we're searching for, and here you see how, you know, we're not doing fully model independent searches, but maybe we make a few assumptions and we can get a lot of leverage out of that. So if this is the kind of thing you're searching for, you know, what are some other interesting features in this kind of event, or in this kind of signal? So this is a Z prime that decays to two, say, scalars, X and Y. Different, let's allow them to be different, and then X and Y each decay to two jets, or two quarks. Anyone think of any features, additional features? We call our features X, right? Go ahead and throw one out if you can think of one. Yes? Okay, PT of each jet, sure, why not? PT of jet 2. Any other? You have an idea? Go. Delta R of two jets, okay, sure. Like that, yeah? Ah, we have some real collider people in the audience, good. Anyone else? No? So this is jet 1 and this is jet 2. I mean, okay, why stop at the PT? You can keep going. Jet 1 and jet 2 have other properties, right? Yeah, so why not mass of jet 1, mass of jet 2? Is there one sort of more advanced thing that we've covered in these lectures, which maybe went by too fast for you, but these are, let me give you all the keywords. These are highly boosted jets, right? They're like W's or Higgses or Z's. Yeah, they're highly boosted with two-prong substructure. Thank you, yes. So there's N sub jettiness, in particular one that measures tau, two-prong substructure. Okay, and you know, you could keep going if you really wanted to. There could be more, I don't know, like eta of the two jets maybe, or that's sort of encoded there maybe. Good, okay, so that's sort of the spirit of this, like what else could we bump hunt in? So for this signal, it turns out it's well separated from the background, at least in these two features. Maybe in these two, we didn't try these two actually. So we actually tried these four. So we tried X being four-dimensional. And so in the R&D data set, I think this was 500 GeV, and this was 100 GeV in mass. Okay, and this was like 3.5 TeV. Those are just some arbitrary things we chose. Okay, and so MJ1 and MJ2 also show a bump relative to the background. So this would be MJ1, and this would be MJ2. They also show bumps. Okay.
So can you explain how this some of the background that can get this kind of mass?
How the standard model background could get this kind of mass?
Yeah.
Jet mass. Oh, well, no, so jets are not massless, right? Because of radiation, FSR. They acquire a mass through radiation. So the jet mass, just like MJJ, well, yeah, no. So, okay, this is the jet mass spectrum of QCD is just a power law, basically, featureless. Mm-hmm. Yeah, like the Sudakov factors and all that stuff, yeah. So, right, so because QCD likes to spray things out, that gives the jets a non-zero mass, even though they came from presumably massless quarks and gluons. They acquire a mass through radiation. Yep, good. So yeah, so that's the spirit is like, can we bump hunt in more than one dimension at once? Okay, and that's what this koala hunting, oh sorry, so when you apply koala to a bump hunt, okay, so you would want to train the features X in the sidebands and in the signal region, okay, to learn this likelihood ratio. So koala plus bump hunt is called koala hunting. Okay, so we heard about this also from Ben and Atlas. So they did a proof of concept in, do I have the reference? Anyway, they did a proof of concept. And then Ben is on Atlas, and he shepherded the first koala hunting search through Atlas. Okay, good. Yes? Good, so yeah, so how would you apply it? You'd have to think of how to apply it to a Higgs search. You'd need additional features other than M gamma gamma or something. Yeah, you would need to, as far as I know, nothing public has been done by any of the experiments, nor any, I'm not aware of any theory paper showing how you could do that. But yeah, I think it's an interesting idea, like how could we test out these methods on standard model processes to convince ourselves that they're working. Yeah. Mm-hmm.
So, as you know, this is probably there is a lot of innovative idea in terms of machine learning, but as you know, this sideband subtraction is already been used already for a long time, right? So I guess is this simply the machine learning version of the sideband subtraction?
Okay, so yeah, good. So I can say what I want to say next. Which is, yeah, so this one-dimensional bump hunt has been done for ages, and we've discovered all sorts of cool stuff with it. And what this is like learning this classifier in the auxiliary space. What do I do with that? Okay, so so let's say my situation is like this. Background plus a little bit of signal. Then this is actually equal to P background in the signal region. Maybe 1 minus epsilon to keep things normalized, plus epsilon P signal. All right, just doing a little bit of math here, yeah? So you can see that this cancels out. If I've learned it perfectly, it cancels out. And my anomaly score is just this. So this, I think, is really cool. It's like we got something for free. What is this? It's the likelihood ratio between the signal, and I don't even know what the signal is. I haven't told you what the signal is. Any signal. So it's the likelihood ratio between whatever the signal is and the background. And as we know, that is the optimal classifier for signal versus background. That's why this is the idealized anomaly detector. It is the best you can do if you have like infinite statistics and a perfect model of everything. It is the best you can do to discover any anomaly in that sense.
But you can do exactly the same thing with the conventional log likelihood ratio test, right? You can define some kind of likelihood function, right? It doesn't have to be, you don't have to use machine learning. So isn't that something similar?
Let's see. So if you're saying, suppose I had, okay, the question was, can I do something with the, just the traditional log likelihood function? I don't completely understand what you're asking, but maybe you're saying if I had just, so the log likelihood of what? Like P background, I guess, or P data?
I guess I might have to use the Fourier normalization lens, right?
Yeah.
You need some kind of likelihood, but you are, I see, so in the case that you know the signal.
If you know the likelihood and it's a function of the parameters, but the parameters of what? Here I haven't even told you what the signal is.
No, but
right?
Okay. So I
Yeah.
don't have to go back to your finite diagram.
Mm-hmm.
I mean, that is my assumption. Probably I will be using the matrix element as my likelihood. So that's not what you're saying.
Yeah, I mean, that would depend on parameters, like the masses of these x and y. So here we're doing things without saying what the way in which this baby version of everything is model independent is I don't have to tell you what mx and my are. It can scan over all possible x and y at once. Yeah.
Here you assume that some kind of event first, right?
Event what?
Event first is a Python diagram.
Yeah. To lay out this story, we did say let's suppose we're interested in this kind of events. Yeah. But you can imagine a future version of this where you assume less. That's the dream. Like the ultimate version of this, what's the ultimate version of this? It's always good to keep in mind the dream, right? The ultimate version would be, I don't care what the topology is. My event has, 600 particles in it. I feed all of those features, so low-level features, to my koala hunting classifier.
That would be very difficult because you cannot imagine what kind of background to inside this.
No. I mean, if I had enough data and my classifier was perfect, et cetera, and the control region was perfect, that would work. Yeah, that would find anything. That's the dream. Okay, so good. So with this R of x, which is monotonic with the signal to background likelihood ratio, now is a classifier for signal to background, for unknown signal. So I can cut on that, just like we did with our binary classifiers, our top taggers. We can cut on that, and so we can reject background and keep signal. Yeah? So if we cut on R greater than RC, so R of x greater than RC, what this bump hunt could become, it could become maybe we reject a lot of our background and we keep a lot of our signal so we can grow the bump. We can enhance the bump. Yeah? And let's see. So the last thing I want to, I'm actually running out of time. So I'm going too slow. So if I imagine, so my background, let's say with a cut of R of x greater than something, I have a background efficiency. So the background goes down by some factor. That's the background efficiency. And I have some signal efficiency. Okay, the signal, maybe I keep 70% of the signal and I reject 999 out of every 1,000 backgrounds. Okay, so we can measure how good our method is using a metric called significance improvement. So before I do anything, if I just do the traditional bump hunt, maybe I have n signal and I have n background in the signal region. So my naive significance would be this. Okay, that's the Poisson error, right, on the background. And after I do a cut on the anomaly detector, I get this in the signal region, right? So this is equal to, call this thing significance initial. This is equal to significance initial times epsilon s over square root of epsilon b. Okay, and so this is a multiplicative factor. It doesn't matter what my initial significance was. This is the significance improvement. Is there a question? No? Okay. So good. So that is, if this number is large, that means I've grown my bump. Well, if this number is greater than 1, it means I've made my bump bigger by doing this anomaly detection thing. Okay, good. So I think I've said everything I want to say about how koala hunting works. Now I have, okay, I'm going to tell you now about the other ideas we've had. So koala hunting is great if the background in the sidebands matches the background in the signal region in these features. Yeah? But if there's anything off, any correlations in these features with MJJ, then koala hunting will break. So we came up with some ideas using density estimators, which get around that. Okay. So the first is anomaly detection with density estimation. So anode, that's something Ben and I did. And we were playing around with these normalizing flows and realized that you could train a normalizing flow or your favorite conditional density estimator to learn P data of X conditioned on MJJ for MJJ in the sideband. And then through the magic of these neural networks, so that it never saw, so this is equal to P background, because in the sideband we assume there's no signal, right? So, but through the magic of these neural networks and normalizing flows, it never saw MJJ in the signal region, so we train this normalizing flow here, okay, to learn this distribution. It never saw the data in here, but it can interpolate. So it interpolates automatically into MJJ in the signal region. So then through this automatic, like by automatic, I literally mean you get some function out of this training, and you can ask, what is the value of this function for MJJ in the signal region? It'll give you some number.
I have a question.
Yes?
Okay, so I understand that this is kind of strongly related to interpolation.
Mm-hmm. So strongly related to what?
Interpolation, right?
Interpolation, yeah.
But yeah, as you said, there are multidimensional observers.
Right.
So, for example, if there are some observer which is bounded, bounded,
Mm-hmm.
even though you have sideband, the MJJ, for the other variable which you may consider, that also is bounded. So
Mm-hmm.
in terms of that variable, maybe you are trying to explore it.
Mm-hmm. Extrapolate?
Yeah.
Yeah. So, okay.
And then it can, right?
Mm-hmm. Right, so so as long as things are relatively smooth and this window is not too large, this will work.
In terms of that dimension, that variable,
Yeah.
will be fine, but
Mm-hmm.
you will add, you're looking to the multi-dimensional observer, right?
Mhm. Yeah.
To optimize the plot.
Mhm.
Then some of these other variable maybe is bounded. Then for this network, they try to incorporate this MJJ, but they try to explore for the other variable.
Yeah.
Right? That we don't know.
We don't know, yeah. So I'll describe the one thing you can do to check, though, how good you're doing in a second. Okay, but I think that's a valid concern is, how do you know this thing is working? So, but yeah, so this is what we tried to do, and at least for this case, we found that it worked well. Okay, so you can learn the background density in the signal region this way by interpolating from the sideband. And then, so this, we train one normalizing flow to do this. We train another to learn P data for X in the signal region. So we train two normalizing flows, and then we just take the ratio directly. And then we do the same thing as koala hunting. Okay, and the advantage of this is because of this interpolation, if the features X are correlated with MJJ somehow, the interpolation could hope to learn that correlation or reproduce that correlation. So we showed that even when we make X correlated with MJJ, anode continues to work, but koala hunting fails. But the downside of anode is we have to learn two density estimators, and density estimators are hard, classifiers are easy. So if your features are not correlated with MJJ, we show that koala hunting outperforms anode. Okay, and the last thing we did, do you mind if I go like 5 minutes over? Okay. Okay. So, yes?
Do you learn two different normalizing flows for two densities?
Exactly. So we fit normalizing flow. This is normalizing flow 1. And here we do normalizing flow 2. Yeah. Both of them are in X space. Yeah. Yeah. Good. Okay. So this was a proof of concept. So we just said, okay, let's do a toy data set where we put the signal here, and let's choose our signal region like perfectly to be around that. Of course, in real life, you would want to do this in you would want to scan over the signal region. And you might want to also do multiple versions with different signal region widths to capture, narrow resonances or wide resonances. So yeah, that's how you would do it, carry this out forward in a full analysis. Yeah, good. Okay, so the last thing I want to tell you is a paper that Gregor and I and Ben and a bunch of other people, Claudius, came up with, which is we called Classifying Anomalies through Outer Density Estimation. Sorry, it's a little bit tortured. Cathode, okay? So we realized that you don't have to train the second density estimator. And we could actually combine the best of anode and koala hunting to get both of their strengths and neither of their weaknesses, if you like. So what we realized is with just the first density estimator, you get a model for the background. And then, okay, it's only 4-dimensional in our case, so why not just sample from it? You might say that's obvious, but it took us like a year to figure that out. So why not sample from NF1 in the signal region, then you get background events. So if you like, it's a way of producing background Monte Carlo in a purely data-driven way. Yeah? And in fact, you can sample as many background events as you want in principle. You don't have to be restricted to how many background events are really there. So we show that this has more benefits because you can oversample the background. And then what would I do with these background events? Surely you must know by now. Now I have background events, say a gazillion of them, and data in the signal region. What am I supposed to do? You know the answer. Right. So supposed to train a classifier, right? So classifier, so the koala classifier between signal region data and signal region. We call this synthetic background because it's not the real background. Okay, signal region synthetic background. So classifiers are easier than density estimators. We save ourselves one density estimator, and we get the interpolation robustness against correlations. So this combines the strengths of koala and anode.
So when you say the classifier between signal, data, you mean actually data, right? You don't know whether there is data or not. Sorry, you don't know whether there is a signal in the data or not.
That's right. So if there's no data, if there's no signal in the data, in the signal region, and the background is perfect, this classifier will be fully confused and will not find anything. That's the idea, yeah. So, okay, so just to finish, let me show you one plot. Okay, great. So this is our cathode paper, and let me just show you this one plot, because I think this really summarizes a lot of things that we've been talking about these overdensities. So just focus on the left plot. This is the significance improvement that I'm telling you about. And we, just as a benchmark point, we studied a toy data set that has roughly initial significance of roughly 1 or 2 sigma. Okay, so if you just did a vanilla one-dimensional bump hunt, you would not report anything interesting. You would say I have a 2 sigma upward fluctuation in this mass window. Okay, so it would not be a discovery, right? And then here's the significance improvement of anode. Oh no, sorry, sorry, I'm showing you the wrong plot. That's with correlations. This is the right, oops. This is the right plot. Okay, so this is comparing all these different methods on the same toy data set. And as you can see, anode performs the worst in this case because these features we chose are fairly uncorrelated with MJJ, and koala performs a little bit better. But actually notice the value of the SIC here, the significance improvement, at its maximum. If you could choose the cut perfectly, or optimally, you would enhance, even with the worst method here, anode, you would enhance the significance by a factor, nominally, by a factor of like 7. So you could take our 2 sigma excess and grow it to 14 sigma. And I think that's really exciting. Like that could be hiding in the data right now, you know? And if we don't have the right way of looking for it, we would miss it. We would only say it's a 2 sigma excess, nothing to write home about. When it's actually sitting in the data with, you know, if you look at it for it the right way, you know, with 14 sigma. And then, but then it gets much better. You see, this is what you can do with cathode. So you can get 15, factor of like 15 significance improvement. It starts to get a bit ridiculous, but nominally you could make it a 30 sigma excess. Yeah. Of course, at that point, the sigmas don't mean anything, and it's probably systematics, limited, et cetera. And then also you can see this is the idealized anomaly detector, because we generated this toy data, so we know what the true background is, at least at the sample level. So we trained our own idealized anomaly detector, and you can see that cathode is basically saturating that. So at least on this problem, this R&D data set, what we found is close to optimal. So yeah, so I think that's all I wanted to say. Hopefully you find this inspiring and interesting and are motivated to learn more about these things. And I think this is the things we've been talking about, like top tagging and calorimeters, and these are examples, just some examples, like our own, the things we like. But there's many more other examples out there of the power of machine learning. Yeah, and I think this is a pretty cool way to go and look for new physics.
What do you mean by supervised?
Sorry?
Supervised.
Oh yeah, so we also trained a fully supervised classifier between the signal and the background. So it does better than the idealized one just because we have finite statistics. Yeah. So you have like so we only injected, to be concrete, we only injected 1,000 signal events into the toy data. So with fully supervised, we train it on all the signal we generated. That's like 100,000 signal events. That they're not in the data, but you know, we have the signal events. So we train fully supervised, and that's going to do better because it sees way more signal. Yeah, so it can learn all the correlations better. Yep. Cool. So yeah, and just to finish with an advertisement, if you're interested in this stuff and you want to learn more or you want to contribute a paper, we're going to be opening the registration for ML for Jets which is a pretty cool conference where all this stuff gets done and talked about. And we're going to be hosting it at Rutgers this November. So hope to see you all there. Yeah. Okay.
Yeah,
Thanks.
thank you very much. So we had many questions during the lecture, but any pressing questions?
What's that?
By lecturer, right?
So you should give a question.
That's right, yeah. Yeah, feel free to, just like Gregor said, feel free to email me, or I don't have Twitter, I don't know what that is, but you can email me with any thoughts you have or questions. And yeah, hope you got something out of this.
Do you think that it is possible to catch up the supervised learning through this Anomaly Detection?
Oh, yeah, so I wasn't there, but apparently there was this workshop where a bunch of statisticians, Manuel told me about this. A bunch of statisticians told us that actually they know about this idealized anomaly detector thing since the dawn of time. And they've proven theorems that say if you have infinite data or something, they should be the same. Is that a correct characterization of what they said? I didn't attend.
So the workshop you're referring to was the Christoph anomalies. If people want to Google for that, it's relatively easy to find. But I think the key result was, as you said, with the extra statement that depending on the type of outlier, there might be stuff that has a slightly, there might be other things to do than a classifier that might even be better. Because, let's say, there's a bit of a gap between the statisticians and the application, so it might need a bit of work to get it to actually work, but it's an interesting direction to what we're looking at. So the talks around outlier, I think you can look at that.
Phi-stat, yeah? Phi-stat? P-H-Y-S-stat, yeah. Yeah, but my very layman's understanding of it is if you did have enough data, you could hope that this idealized anomaly detector became the supervised one, yeah. So one thing we don't lack for at the LHC is data. So, maybe things will get better the longer we run, yeah.
Okay, so why don't we thank Professor Shih and then Professor Kazieska again for the other lectures.